Okay, let's go and get started today. I was going to hand out those wireless chips or wireless modules. I think we'll wait till next class to do that lab, since I just want to get through I2C as a follow-up to SPI that we did last time. So we're going to do this today, and then we'll have that lab, that next lab, talking to those wireless modules next week. So let's go and get through our lecture today. So today's topic is synchronous communication again, but this time with a system called I2C or I2C or IC. Now, before we do that, a quick review of synchronous communication. We've done this before. Let's go through it again. Synchronous communication, the two things that are exchanging data, the two nodes that are exchanging data, have to share some clock signal that they both look at. And in the case of I2C, just like with SPI, that's the case. So there's going to be data going on one wire in I2C and a clock signal on another wire. Now, even though it's the same kind of general concept as SPI, there's some key differences that we're going to see here in just a second. So quick review of SPI. Essentially, SPI had these 4 wires, a clock, MOSI, MISO, and then a slave select. And the slave device, when the slave select went low and the clock ticked, a bit came out of MOSI and went into MISO. So in other words, it just exchanged 2 bits. The next time the clock ticks, it exchanges 2 other bits. And essentially, it's 2 shift registers that are hooked in a circle, and it just exchanges that. So after 8 clock ticks, the data would have been completely exchanged between the 2 registers. So in other words, if you imagine bit 0 marching across 8 times, 3, 4, 5, 6, 7, well, 1, 2, 3, 4, 5, 6, 7, 8. Notice this bit 0 will now wind up over there. And if this one here marches across 8 positions, 1, 2, 3, 4, 5, 6, 7, and then 8, it's over here. So it's essentially after 8 clock ticks, the 2 communication ends completely exchange data. And that was how SPI worked. But one of the things you may have noticed when we looked at the data sheets and the transaction sequences is there are a lot of cases where, for example, this shifted out the address on a read, and then the data came back in the next 8 clock pulses from that device. And then on a write, nothing ever came back from the device because we were writing data to it. So one of the things to note is that on an SPI read, both data lines carry data, but not at the same time. In other words, when we're shifting data out here to say what address we want to read, and then these are dummy pulses here where the data doesn't even matter, and all we care about is the data that comes back in. And on the other side, when we do an SPI write, we're just shifting data out and then shifting more data out. And we don't really care about what comes back because nothing useful is coming back because we're talking to it. So the idea there is in SPI is we have this extra data line, but a lot of the times we're only using one data line or the other data line. So what happens in I2C is they decided, well, if the goal is to reduce the number of wires that we need, or the number of lines, or the complexity of this, then why not get rid of those lines and have a single data line that sometimes acts as an output and other times acts as an input. So in other words, it'll be an output when we're sending data out from the master, but then when we go to read, we switch it and we listen on that one. So kind of like you can think of it kind of like a telephone that you talk and the other person listens, and then you listen and the other person talks. So maybe more like a walkie-talkie that you key it and you talk, and then you let off the key and you listen. So anyway, that's one of the key differences between SPI and I2C. SPI required 4 wires, as we saw last time. I2C only requires 2 wires, just a clock and a single data line. Also no slave select. But both are still synchronous. In other words, they both have this shared clock. In this case, it's called the SCK, or sometimes other things, SCLK sometimes in SPI terminology. But in I2C terminology, it's always called SCL. And the data line is always called SDA. And that data line can send data sometimes, receive data other times. But it's still synchronous. They both share a clock, and the master generates the clock signal in these cases, both cases. Okay, so let's take a quick look at I2C in a little more depth there. So that we have those two lines. The SCL line is the serial clock. And again, that clock is generated by what the master device, the bus master. And then there's SDA, which is a serial data line. And that's bidirectional, meaning it's used by both the master to send data out and the slave to send data out. And each of them will listen or receive off that same line at certain times. So unlike SPI, or like SPI, it's synchronous, there's a shared clock. Unlike SPI, there's no select line. And how do we get around a select line? Well, each node has what they call a device address. So when we clock in the first byte of data, and we'll see that here in a second, that device address, if it matches our chip then responds to the data that follows. If it doesn't match, the chip goes back to ignoring the rest of that message. So instead of a select line, there's an address that's part of the message. Now that has good things and bad things associated with it. For example, it's good because we don't have to have an extra I/O line for every device. We don't have to have a select line for every device like we have to have in SPI. SPI, we have like 10 devices we want to connect to an SPI bus. We need 10 I/O lines, a slave select for each one. And we could play some games with logic circuits to make it so we could get by with, I don't know, 3 lines and 8 devices that we select or something like that. Or 4 lines and 16 devices we can select. 2 lines and 4 devices. We could use some sort of decoder chip to as logic to reduce the number, but still each device has its own select line. In I2C, no device has a select line because they each have an internal address node. And most chips, those are programmed in the factory. Sometimes there's a pin that lets you select between 2 different ones. But most of the time they're programmed at the factory. They're built, they're designed to respond to their address. Now, unlike I2C, only one data line is used, and it's bidirectional, which means that we have half duplex communication instead of full duplex. But in SPI, most of the time we're not using the full duplex capability anyway. Sometimes you do, like in the case of that wireless module we looked at. But for the most part, you're requesting data and reading it, or sending data to an address and then writing it. And so it's half duplex is how I2C works, and most of the time SPI is as well, at least functionally, even though not physically. Also, the data line and actually the clock line both are what are called open drain. And what open drain means is that means if you think of the voltage on a line, the open drain basically means you can pull those lines low, but then when you let go of it, they'll get pulled back high. They have what's called a pull-up resistor that's attached to the 2 lines, either inside of a device or a lot of times externally. It's up to you to add the pull-up resistors. But that means the pull-up resistors, if nothing is pulling the line low, nothing's forcing the line low, it just gets pulled up by the resistors, whatever voltage the resistors are connected to. So in other words, open drain, if you think about that, it kind of means like, imagine you have a drain in your sink, but it drains kind of slowly. And so you can turn the water on and the level will go up, but when you turn the water off, it'll slowly sink back down to being empty again. So the default state in this case, though, rather than being empty, is full. It's high. It's a pull-up resistor, so the voltage is high. And at idle on both SCA or SDL and SCO, SDA, SCO. And when one of the devices activates that line and drives it, they either leave it alone, leave it high, or they grab it and they pull it low. Think of it like a switch to ground. You connect that to ground, it then sees the voltage of ground. When you release it, it sees the voltage through the pull-up resistor and goes back high again. And those resistors usually have can have pretty high values. It's usually like 4.7 k ohm resistors, 10 k ohm resistors. Usually 4.7 k, but you could have different values specified or maybe needed depending on the length of the wire and the built-in capacitance of the wire and things like that. But and don't worry too much about that. Just know that the lines are either going to be driven low or they're going to be let go to go back high. But the end effect of that is that that means those lines can be shared by multiple slave nodes, even though these are bidirectional. So in other words, you'll never have one trying to force it high and the other one trying to force it low and have the case where you burn something up. You can't have that with an open drain system because either they're both pulling it low. And one way to think about it, you might think about kind of like if you've ever ridden on a bus or a trolley car and they have that wire that goes along the top and you can pull it to activate the signal to say you want to stop and get off. So you can pull it and it turns on the little light, maybe makes a little bell ring, and then when you release it, it goes back to not doing that. So it's kind of like that is how open drain wires work. But the reason they implement it that way on those buses is so everybody in every seat can have access to that one line and share it to have one signal that's shared between them. Okay, so I2C uses fewer wires and pins, but it also, because it has to have the addressing built into part of the data that's sent, it also means it tends to run slower than most SPI systems. And we'll get back to the speed of I2C in just a second here. But first off, here, I2C bus states. Looking at the bus states, it defines several bus states and conditions. Because it doesn't have a select line and it only has the one data line, they came up with this clever way to know when a message was starting and when it was stopping and when it was data in between the start and the stop. And they did this. On idle, both lines are high. That makes sense. Nobody's pulling on the little rope. Nobody's driving a signal. They're just sitting there high. And what happens is, to start off the transaction, we have a start condition. And what start condition is, or a start state, is you leave the clock line high, but then you pull the data line low. And it's the master that's doing that. So the master says, leave the clock high, pull the data line low. So let's say here, this is SCL here. This is SDA. So you'll pull the SDA low while leaving SCL high. And the chip on the other end says, oh, that's a start condition whenever I see that falling edge on SDA where SCL is forced high. Now, then we would send some data. We'll talk about that in a little bit. But then on the other end, to say now we're done using the bus, we have a stop condition. What the stop condition does is it leaves SCL high again, but now it sets SDA high again. So it lets SDA go, and it goes back high with SCL high. That's a stop condition. Now, in between the start and the stop, we have data bits that are sent. And essentially what we do is data is placed on the SDA line whenever the clock is low. So the clock gets pulled low, we put data on the line, we set the clock high. When the clock goes high, whatever the receiving end is on the slave reads the data when it sees that clock go high, and then we pull it low, put more data on the line, put it back high. And so it's kind of like it runs in lockstep, but both the high pulse means something and the low pulse means something. But one of the things you'll notice is that the data line never changes when the clock is in the high state during the data period. And that is how those changing the data line is not ever going to get confused with a start condition and stop condition, because these only happen, SDA is changing when SCL is high. So all of the changes here are made when SCL is low. And that can be important. We're going to look at a graph of this and it'll make a little more sense, I think, in a little bit. One other thing that's important to note is that every 8-bit block of bits that is transferred also has an acknowledge on the end. And the acknowledge comes from the end that's doing the receiving. So if you're sending out data from the master to the slave says, yeah, I got that. And that's something that SPI didn't really have either. SPI had no way of knowing if you sent out or clocked out some data. You had no way of knowing if it got received or if the chip died or the lines got severed. You would just clock stuff out and look at what came back. But with I2C, every single block of 8 bits, there's an acknowledge or a negative acknowledge from the other end. And sometimes there's logic associated with those where the device will negative acknowledge on purpose, or the master might negative acknowledge saying, I don't want any more data from you. But for the most part, the acknowledge is used to say, yes, I got what you just sent me. It also has a use that we'll see later on for a thing called clock stretching, which can give the slave device time to do some processing or take some kind of measurement or some sort of action. Also something that we didn't have in SPI. So one of the things that's really cool about I2C is it uses a really small number of wires, only uses 2 wires, but it has some fairly sophisticated handshaking and acknowledgement stuff built in to that with just those 2 wires. It's a very clever technique. Okay, so moving ahead here, We talked about speeds earlier a little bit, but they are slower than the standardized speeds for I2C are slower than what we would generally see for SPI. And part of that is that in order to detect the start condition and the stop condition, and in order to also the overhead of having the extra addressing byte at the beginning of every bus transaction can really make things much slower. But essentially, the maximum or the clock rates of standards that are defined for I2C are 100 kilohertz, which is considered standard mode or standard speed, 400 kilohertz, which is considered a fast mode device, and then there are some newer devices that are 3.4 megahertz, which is high speed mode or a high speed mode I2C device. Now, most of the devices that I've seen recently are 400 kilohertz, and you can always go lower than the speed. The speed can go slower without any problem. But 400 kilohertz is what they guarantee it'll work at for most devices. There are some high-speed devices, but you'll notice that when we talked about SPI last time, we had devices that were like 10 megahertz. Notice that even with the highest speed mode of I2C, 3.4 megahertz, and you can overclock these a lot of times without hurting anything, but one of the things that slows these down is also that open drain thing, that we're just letting the line go and letting it drift back to a high level rather than actively forcing it high and forcing it low. And that can slow things down because when we let go of that line, we're at the mercy of the electrons flowing through that pull-up resistor and whatever line capacitance and length of wire and whatever it takes for that to build up till it gets up there. And we can't run that at an arbitrarily fast rate just because of laws of physics. Okay. And if you're implementing a device, look at the data sheet. It'll specify what the maximum rate is or which of these modes it supports. Most cases, you'll see 400 kilohertz supported, and you can always run those slower if you want to. Okay, now the complete message format here, it works like this. So you basically say the line is idle, meaning both of the lines are high, both wires are high, SDA is high, SCL is high. But then a start condition starts off a message, in which case SCL stays high, but we have a falling edge on SDA. After that, now we're ready to have what's called the address frame. And the address frame is essentially 8 bits of data plus an acknowledgement period. And the 8 bits of data have 7 of those are an address, followed by a read/write bit, which is 1 on read, 0 on write. And then the acknowledge comes from the slave going back the other direction saying, yes, I got this address frame. Now, one of the things to note is that it will not acknowledge if the address doesn't match the device's address. In other words, it doesn't just get that and say, yeah, I got that even if it wasn't for it. And that can be a way that I2C systems can be designed so you can actually query the bus and say, hey, temperature sensor, are you out there? And it'll say, yeah, I got that. I'm here. And so you can tell immediately, just after this first 8 bits get clocked out, was that device that I think is there actually there, or is it not there? And if it says, yes, I'm here, you know that it's there, and then you can talk to it. Now, after this first address frame, we now have any other data frames. It could be data from the master on a write. It could be data from a read from the slave. But somebody's going to take over the line, and either the master is going to drive the line or the slave is going to drive the line. And then whoever is receiving that data, it's up to them to then acknowledge, yeah, I got that. So notice a little bit of additional reliability built into this. But after we send any data frames, 1 or more data frames to that device, we send a stop condition. And the stop condition, put SCL high, and then raise SDA from low to high. And then that's it. That's an entire transaction. So generally, start condition, address frame. If the address frame matches, then we get an acknowledgement. If we get that acknowledgement, then we move on to either doing a read or a write, depending on what we said we were going to do in the address frame. And we either clock the data in, or we push the data out onto SDA, and then we either send an acknowledgement if we clocked it in, or we listen for the acknowledgement if we clocked it out. And then we know that they got that byte, we know that they got that byte, or they know we got that byte, and then at that point we then say, okay, stop, I'm now done with the bus, and that frees the bus up now to go back to the idle state with both of the things actually high. Notice that naturally finishes it. SCL is high, SDA goes to high, it finishes naturally in that idle state. Okay, a quick thing about the acknowledge at the end. That acknowledge bit is always asserted by the node that's receiving that frame of data. So the first one, that address frame back here, this acknowledge will be from the slave. The second frame, if we're doing a write, it'll be from the slave. If we're doing a read, the acknowledge is up to the master to perform the acknowledge. So 0 means the frame was received. 1 means the frame was not received. Now those might seem backwards, but if you can probably think about what the reason for that would be. And the reason for that is primarily that think about what's the idle state of the line if nobody's driving it? It's 1. So you wouldn't want to use that for an acknowledge because that would be the same as nobody being out there. So you need to have the line be low for the acknowledge because the idle state is 1. So that way we can distinguish between the idle state and an actual acknowledge. But if the line is pulled low during the acknowledge bit period, then we know that frame has been received. If the acknowledge bit is 1, then nobody acknowledged that particular frame. Also, one thing that is possible with the acknowledge, it also serves as a form of handshaking or flow control, that if the slave grabs the acknowledge and says, yes, I got that, and it holds that line low, even after the clock on the master finishes ticking, if there should be something in there that watches the acknowledge and waits for it to go back high again to say, okay, they're done acknowledging. And that is used a lot on a device to do what's called clock stretching. In other words, if you want to slow down the master, there needs to be some way for the slave to say, hold on a second, I'm working on something. And that's the way it does it. It'll pull that ACK line low saying, yeah, I got that, hold on. And then it can release the acknowledge line and then be ready for other data. And that can happen a lot when you're doing a read from a device. Let's say you're reading from a device and you say, hey, pressure sensor, I want to know what the pressure is. And it's in the middle of the calculation for it. It doesn't have the data ready. It'll say, okay, I got your request. I'm computing it, and I'm done acknowledging, and now I'm ready to clock out the data that I had from that. And so any good implementation of I2C will have clock stretching built into it. Now, some devices don't do that. Some sensors or nodes, slave nodes, just don't. There's no need for it, but some of them do. And so you got to be careful if you're writing a software implementation of this, build in clock stretching. Now, let's put all that together and look at an actual waveform here. So here's an actual transaction. This is only 2 frames long. So here's the first one. So SCL and SDA. So SDA is on the top, SCL is on the bottom. So if we start looking through this, you might notice there's the start condition. SDA going low, while SCL is high. Here's the start condition. Actually, it's more over here. SCL high, SDA going low. It's right there. So that starts us off. And then 1 bit period later, notice we haven't changed the SDA. We're not changing the SDA line when the clock is low, but when this goes back high, we put the first address bit on there, meaning the most significant one. Clock goes back low. And again, it sets up the data while the clock is low. This data is sampled on this falling edge when that's high. So the clock goes low, we change the data. Clock goes high. Other end reads the data. Clock goes low, we change the data. So this crisscross between bit 6 and 5 and 4 and 3, it always happens when the clock is low here. In other words, the line never, if we look at the high part here, the little plateaus on the top of this, there's never a case where the data is changing when that's high, except for the start condition and the stop condition. Okay, anyway, we clock out all the data. So that's 7 bits worth of address, followed by 1 read not write bit, read/write bit, followed by the acknowledge. Now, and then when all of this is done, here's our stop condition over here. Again, that's the line, the data line going high when SCL is high. All right, so we have the master sending out the 7 device address bits. We have the master sending out the saying whether it's reading from that device with that address or writing to that device with that address. We have the acknowledge from the slave that's saying, yes, I got this frame and it was for me. My address matches that frame. I'm good to go. I'm good for you to either read to me or write to me or read from me. And then we have this next period here. Again, the clock or the data line changes states only when this is low. And now we're ready for the next bit. The next bit goes on the line. Clock line goes high, and now we have our 8 data bits, which if it's a read, that's going to come from the slave. If it's a write, it's going to come from the master. And then at the end of that, we have the acknowledge from whoever was receiving that data saying, yes, I got that. So there's a lot, it's just 2 lines, but there's a lot of really cool stuff going on here with the being able to acknowledge, being able to have multiple devices all on this at one time, and so forth. Now, one thing about I2C transactions is they're not necessarily always 2 bytes long like we have here. It might be that we say, hey, I want to read from this device, or I might want to write the address to be this, and then I want to read from that address and read 1 byte, and then another byte, and another byte. So the transaction might have additional bytes before the stop condition. And a lot of devices will automatically increment through some internal register address. So you could say, hey, I want to read from address 0. And then if you do another 8 bits, it'll be register 1. And another 8 bits, it'll be register 2. So you can actually clock through or read through every one of the register addresses by all in one big I2C transaction like that. So that essentially allows us to send or receive multiple bytes in one transaction, either write more than one or read more than one. And we'll see that in some of the data sheets here in just a second when we look at that. Okay, now moving on here, let's take a look at the data sheet for a device. And we actually looked at this device last time, but we looked at it, it's SPI, the SPI part of the data sheet for it. But you'll notice in the data sheet, it's I2C or SPI. It can actually do both. You can hook it up one or the other, either way. All right, so let's go take a look at the actual data sheet for this. So give me a second to switch over to that. And we're going to look at the the I2C section of that data sheet. So here's the data sheet, same one we looked at last time. And this is just a little 3-axis accelerometer, digital accelerometer. And there it is talking about I2C. So we're going to scroll down to the I2C section, which unfortunately these are not clickable. So we'll just have to go to page 24 here. And if you want to follow along at home, you can bring up this data sheet and go to page 24 yourself. All right, well, before we get to page 24, here's some stuff about the I2C interface here. And you'll notice that it shows the maximum rate here is 400 in fast mode, 400 kilohertz in fast mode, 100 in standard mode. And there's a note on there that says data based on standard I2C protocol requirements. But that is essentially what the fast mode is supported and standard mode. Both of those are supported. And then there's some timing diagrams. We're not going to worry about that. So that would be if we were writing this and had to measure it on a scope, we could make sure everything lines up to make sure reliable transfer happened. But what I'm interested in is that page we were going to, which was 25, I think. We'll get there. Before we do that, here's the pinout. You'll notice that it has a, well, let me go back to that. It has an SCL and an SDA pin label. And these pins share functions with other things if you're using SPI. So let's go to that page 25. Okay, so here we are, I2C serial interface. The device is an I2C bus slave. I2C is employed to write data into registers whose content can be read back. All right, so basically you can write data into registers, you can read data from the registers. Now, the I2C interface is compliant with fast mode, as well as with normal mode. In other words, you can run it slower, but you can also run it up to 400 kilohertz. And they also mention here, both lines must be connected to VDDIO through an external pull-up resistor. When the bus is free, both lines are high. So again, that's that open drain lines that we talked about. And here's I2C operation. And this actually does a pretty good job of describing it. It says the transaction on the bus is started through a start signal. They say that they're going to label that ST going on. A start condition is defined as a high to low transition on the data line while the SCL line is held high, just like every other I2C system. Now, it goes on to talk about that. It says the next, or after this has been transmitted by the master, the bus is considered busy. In other words, it's in the middle of, between a start and a stop. The next byte of data transmitted after the start condition contains the address of the slave in the first 7 bits, and the 8th bit tells whether the master is receiving data or from the slave or transmitting data to the slave. When an address is sent, each device in the system compares the first 7 bits after a start condition with its own address. If they match, the device considers itself addressed by the master. So you kind of think of that like their name. You can say, hey, hey, accelerometer. And it's like, oh, that's me. And then it says, I've been addressed. It acknowledges, and then it goes on. Now, the slave address associated with the LIS2DH12 is 001100. So there's the 6 bits. So that's what address it's looking for. And it actually goes on to say you can actually change its address by 1 bit by taking the SA0 pin and connecting it to the supply voltage, and then it makes it so its address becomes this. Which that could be useful because that allows you to put maybe 2 of these devices on the same I2C bus and have 2 accelerometers for some reason. Or maybe if you had another device that just accidentally happened to have the same address, you could actually address both of them by setting this one to not be the same as the other one. All right, data transfer with acknowledge is mandatory. A transmitter must release the SDA line during the acknowledge pulse. The receiver must then pull the data line low so that it remains stable. Low during the high period of the acknowledge clock pulse. The receiver, which has been addressed, is obliged to enter or to generate an acknowledge after each byte of data is received. So it's just telling us how I2C works essentially right here. And basically says after the start condition, a slave address is sent. Once the slave acknowledgement has been returned, an 8-bit subaddress is transmitted, and so forth. And let's go ahead and take a look at the what the chart looks like here for this. So this is transfer when master is writing 1 byte to slaves. In other words, master sends the start condition. It sends the slave address plus the write bit. The slave then generates the acknowledge bit and sends it back. We then send 8 bits worth of the sub address. The slave acknowledges that it got that. And then we send the actual data that we're writing, the 1 byte of data, 8 bits of data we're writing, to this sub address. And the slave says, yeah, I got that. And then we send the stop condition. So you notice this chart here is mixing this, showing what the master does on the bus, what the slave does on the bus. And it's not as nice as those kind of charts that show the entire waveform of it, but it kind of gives us an idea, an overview of what's happening. So here's what happens when we send multiple bytes. Start, slave address plus write, slave says got it. We send the sub address, slave says got it. We send the data, slave says got it, data, got it, however much data we want to send until we're done, and then the master finally says stop, we're done. And then here's a read sequence, same thing, start, address plus write, got it. This sub thing here is the sub address, it says got it. And this SR is what's called a repeated start. So we send another start again to get us out of write. We send the address again here, plus read this time. And he says, I got that you want to read now. And then it sends us the data the next time. And then the slave or the master at that point then acknowledges and then says stop. And this negative acknowledge at the end means that's the last byte I want from you. And I'm going to stop after that. Notice over here with multiple bytes, it acknowledges, and then after that one says that's the last one I care about, and then stop. And I don't know if there's a waveform for this. Okay, there's waveforms for the SPI, but not for I2C here. But you get the general idea of that. Let's look at, go back to the presentation for just a second here. All right, if we go to electronic component distributor and search for I2C, you're going to find tons and tons of devices that do all the same kinds of things that you saw for SPI. I2C being a little bit slower tends to be used for things like sensors, like temperature sensors and LED control and things like that, memory. If it's something that requires really high speed transfer, you tend not to see it as much with I2C as with SPI. But there are still things that I2C works with, all kinds of things. One of the ones I should probably take off here is SD cards. There are memory cards that work with I2C, but it's not really the SD standard. So I should probably, here while I'm thinking about it, let me go and take that out of there. Okay, but all these other things, there are definitely things that are I2C based that do all of these. All right, a couple other devices. We already looked at that accelerometer. Let's look at a couple other ones here. Let's look at that that MEMS pressure sensor / barometer. Let's just take a quick look at that. Let's look at a memory chip and let's look at this 16-channel LED driver. But there's really just tons and tons of these, but they all follow that standard. Start, address frame, acknowledged, either we're reading or writing, and then the data frames that follow that. And then we're done on the last one. Stop. Condition, bus goes back to waiting or being in the idle state. Very cool, and you can put a whole lot of devices on one I2C bus. There is a limit though, because the number of slave device addresses is limited. It's only a 7-bit address, so that does limit how many devices you could have on one bus. All right, let's look at this pressure sensor. So let me switch back over to that. Oops, I forgot to switch it. Hold on one second. Okay, so here's this pressure sensor. And this is a MEMS pressure sensor. But it's essentially acts as a barometer. In other words, as pressure increases, this little plate gets pushed. The device can sense that. How far that's been pushed, and it associates that with an atmospheric pressure. In other words, when you're sitting in your room right now, you have the weight of the air pressing down on you, and the higher up in altitude you go, the lower the pressure is. So the air gets thinner, there's less molecules sitting on top of you pushing down on you. This can sense that, and this is actually really accurate. It can sense it just a few inches worth of variation. So you could use this for a lot of things, and you'll notice that altimeter and barometer for portable devices, enhanced GPS applications where it wants to know the altitude, weather station equipment so you can see the barometric pressure rising or falling, wearable devices, those are all listed there. But you'll notice that this has an I2C interface, and this is actually made by the same company that made that, accelerometer we just looked at. And so on the same page, close to the same page, you'll notice but it has a different slave address than the other one had, so you can put these together. But notice it's the same kind of process for how you send and receive data. It's actually the same diagrams they used in both of these. So this one maybe isn't as interesting. Let's look at another data sheet. So let's go to that third one on the list, the 24AA02. Let's take a look at that data sheet. So let me switch over to that one. All right, so here's the data sheet for that, and you'll notice again, this is a serial EEPROM, which is a kind of like a flash memory, electrically erasable programmable ROM chip, and it's I2C. This is only 2K worth of memory, so very small amount of memory, but there's another cool feature that this has as well, and that's that it has this pre-programmed node address built into that. So if you have a chip that you want to, or a system you create and you want to put like a unique serial number in each one, They can't be changed. These chips come with a unique serial number already programmed into them, and so you could just read that. And there's a standard for those, that EUI48, EUI64 for storing those unique numbers. So those could be used for all kinds of things, like making sure everything has a unique network address or making sure everything has a unique serial number. They're built in that way. They come from the factory that way. Now, taking a look at the pins for that, notice how simple these are. They have power, VCC, they have ground, VSS, and then they just have the SCL and an SDA line, and that's it. Now, some of the variants of these have the ability to have these address lines set, so you can put more than one of these on a system, but this one up here, notice power, ground, SCL, SDA, that's it. Very simple to wire into a system. And you'll notice the more than 1 million erase write cycles, data retention of greater than 200 years. Let's go to the section that shows I2C at work. You may have noticed that the maximum rate of this was 400 kilohertz, so it's fast mode. Pins have an SCL and an SDA. Okay, so here's the data chart sequence for that. So this is a data chart sequence for writing a byte. So we send the start condition, we send the device address along with these chip select bits here that those other ones have. So notice the start says these are all don't cares for the version that doesn't have those pins. So basically we could put all zeros in there. And then since we're doing a write, we put a 0 in this position. The acknowledge comes from the slave. It says, hey, I got that. I'm at that address. I'm here. And then we clock out the word that we want to write. And then that's the word address that we want to write. So that's like the address of the byte we want to write to. It acknowledges, and then we put the data out that we want to write into that address. And it acknowledges, and now that data has been updated in that memory. And then we say stop at the end by sending the stop condition. Again, notice same thing as with every one of these devices. If we look at the page write, it's the same thing, but we send the address we want to start writing at, and then the first byte, and the next byte, and the next byte, and we can go through and iterate through all of those, or a page of 8, a block of 8 of those bytes for one page, and we'll have written out the entire thing. We've got similar diagrams for reading. There's an address read. For the current address. Here's an address read from from a random address. Here's a sequential read, reading out as many bytes as we want, one after the other. And actually, with this one, you could read out the entire contents of the memory all in one big I2C transaction. You send the start, you send the control byte, the chip acknowledges, and then we get the first piece of data, acknowledge, get the next one, acknowledge, and next acknowledge, and so forth, all the way till we're on the last one. At the last one, we say no more, negative acknowledge, and then we send the stop pulse. Okay, and these do not have a lot of memory in them. These are actually pretty small devices that they really only have 200 or 256 bytes of memory, and the last little bit of it has that address in it, or that unique identifier in there. And so notice that the main use of these is to store some sort of identifying information in something. Like if you had like a print cartridge that when you plug it in, it knows how much ink it has inside of it. This would be the kind of chip that would be in there. It has a serial number and some stuff, and then how much ink is in it. Or we used to have a 3D printer that came with these cassettes that had the filament inside of them. And the cassette, when you plugged that in, it had a little chip inside of there that kept track of how much material was in it. But it also had a serial number. So when the unit went down, it would disable it when it got to a certain level, and then you couldn't re-enable it because the chip would tell it not to. But because it was implemented as an I2C device, you could just hook it up to a microcontroller and reprogram it and refill those spools yourself without having to buy their consumables. But the idea here is this is just a little bit of memory with a unique identifier for a serial number or something like that, and a place you can store things like settings or non-volatile things, or Maybe if it was in something like a cell phone, it might store some unique serial number information or configuration information about whatever hardware you have on that phone. All right, let's look at one more. Let's take a quick look at one final one. Let's look at this 16-channel LED driver. That's a little bit different than what we've looked at before. So I'll just switch over to that. All right, so notice this is a 16-channel I2C bus constant current LED sync driver. And essentially what that's used for is a way to control the brightness of LEDs. And this has 16 channels, so you can hook up 16 LEDs to it. If you look down here at this block diagram, you kind of see that. So in other words, if you had some, I don't know, if you have an Alexa at home and it has that ring of LEDs that go around the outside and they can change colors and they can change brightness, you might use a chip like this to drive those LEDs and have the different colors of them connected to this in some way. But you can talk to this over SPI or I2C. There's an SCL line, there's an SDA line, and you can just send those pulses and get it to do things there over that line. And you can set the brightness of each one individually. Now let's see if we can find the section that talks about the timing requirements. I actually haven't looked at this one carefully, but let's just scroll down and see if we can find. Okay, here's the pinout. And hold on one second here. Okay, so let's finish looking at this data sheet. Here's the chip, there's the SDA, there's the SCL line. Here are all these outputs that you can connect LEDs to that come out of there. And if we scroll down, let's see if there's a little timing chart for this guy. Okay, here's the timing chart for the various parts of SCL, SDA. There's the start condition, so forth. Let's see if there's a diagram that shows how you actually talk to it. Okay, there's a bunch of clock pulses there. Start and stop condition, data in between them, acknowledge. There's some stuff there. Okay, here we go. This is more what we're talking about here. So here is basically you send out the slave address, and then whether you're reading or writing, and then the control register number, and then I guess any data from that would go after that. And so here you just follow what these have here for what you want to write into the different registers. Notice that this is actually a long thing. So in other words, you could say, here's the slave address that I want to write. Here's the control register. This is the pulse width modulation register, which is controlling the brightness. And then if you follow that along, then here's 0, here's 1, and then that continues for all of them. So you could write out with one big I2C transaction, you could write out the brightness for every one of the LEDs that are on there. And then at the end, you basically send the stop condition. So very cool, very useful chip if you're designing something like an Alexa with a light ring. And notice down here, they say that you can actually have more than one device that sits on the I2C bus. And that's true that there's actually a multi-master mode for I2C as well, which is actually really cool, where you can have more than one master that kind of sits on that bus together. And that's something that you can't have as easily with SPI, because one of the devices in SPI has to kind of decide which slave select line to put low for who it's talking to. But in I2C, you could actually have two microprocessors sit there. One of them addresses the other, and they exchange data or they talk to each other. So it's a little more like a network in that respect. Okay, so that's really all I wanted to cover today. So let me go back to the presentation just for a second. Pop. And there. And one thing quickly that, like we did with SPI, you can also implement I2C in software. A lot of times there's a hardware implementation on a microprocessor or microcontroller. Your laptop probably has I2C temperature sensors. maybe fan controllers. Maybe if you have a laptop that has like the LED backlight in the keyboard, and that can be controlled and change the brightness, or it has colors, patterns underneath them that can be changed. A lot of times those would be I2C devices as well. And there's probably hardware in your PC that talks to those, but you can implement it in software with a software I2C function. The only thing I would say about that is you have to have a system that can have open drain I/O lines, or the ability to switch the I/O lines between input and output really easily without having them glitch in some way. Most microcontrollers have the ability to do that pretty easily. The other thing that I would say about that is you have to take care when you implement the start and stop conditions to make sure the timing of those is right and compliant with 100 kilohertz or 400 kilohertz requirements. And also, you should probably implement the clock stretching behavior, where if you're writing the master code in software, that you definitely observe and wait till the acknowledge line is released before moving on. Because if devices that have clock stretching, if you ignore that, you're going to get your data come back as garbage sometimes. So that's it for today. I want you to finish up your labs, and next class, come to the classroom, or let's say come to my office during office hours, and I will give you the little wireless modules we're going to use for that next lab for next week. And that next lab, you're going to talk over an SPI, software SPI connection that you make on the Arduino. You're going to use that to talk to one of these little wireless modules and access its registers. And when you come to my office, I'm going to go ahead and give you, if I have enough of them, I'm going to give you 2 of them. Some of you might want to order those. Again, they're like $1.20 each or whatever. So for the cost of less than you would pay for like a sandwich at lunch, you can have 2 wireless modules that you're going to use for the next few labs in this class. But if you don't want to buy them, I bought some that I can loan you. I'll write down who borrowed them and get them back from you to use in other classes. But come to my office hours next week during normal class time, and I'll give those to you. I'm still going to post a lecture just like today that goes over that lab and gets you started on it, but come and get those supplies. If you want to get them at a different time, just send me an email, make an arrangement. All right, work on your other labs, get those done. And other than that, stay safe, wash your hands, and no new lab this week, today. Have a little break. Everybody stay safe, stay warm, and I'll see you next time.